Hi, I'm Kenny Jones, and I'll be presenting PLAD, a method for learning to infer shape programs by making use of pseudo-labels and approximate distributions. Programs are an appealing and well-studied representation for visual data. They are compact, produce high-fidelity outputs, and can expose higher-order properties. Having access to the procedural form, which generates visual data, supports many downstream applications, such as high-level manipulation and editing, by a person or autonomous agent. Unfortunately, most visual data lacks program annotations, so we desire a method that can infer programs for visual data. Our shape program inference problem assumes the following as input: a domain-specific shape language, L, a black box executor, E, that converts programs from L into shapes, a reconstruction metric, M, that compares the visual similarity of two shapes, and finally, a dataset of shapes from a distribution of interest, X star, that lack known associated programs. Our goal is to learn a recognition model, PZ given X, that can infer programs whose executions achieve high reconstruction accuracies over X star shapes. For our problem statement, reinforcement learning is the de facto approach. The recognition model can be treated as a policy network, and the reconstruction error between the input and the inferred program's output can generate the reward function. A common practice is to start with a model that has been pre-trained on synthetically generated shape program pairs with supervised learning, and then to perform fine-tuning towards a distribution of interest. The main problem with policy gradient RL is its instability due to high variance gradients leading to slow convergence. We present the PLAD framework. PLAD methods create paired shape program data that is used to train the recognition network with maximum likelihood updates. However, as ground truth pair data is unavailable, PLAD methods need to make compromises on either the accuracy of the assigned program labels or the shape distribution. For methods that use pseudo-labels, each program Z is an incorrect label for its paired shape X, so executing Z does not create X. For methods that use an approximate shape distribution, the distribution of shapes X has valid program labels, but this distribution only approximates the distribution of real shapes of interest. One PLAD method is self-training. In self-training, the recognition model is first run over the shapes from X star to infer a set of programs Z. Then, using the reconstruction metric, entries in a data structure are updated to keep track of the best matching discovered program for each shape. Self-training then constructs XZ pair data by assigning labels from the current best program set to shape instances from X star. This XZ pair data can then be used to fine-tune the recognition model with MLE updates. PLAD methods can be initialized with a pre-training phase on synthetically generated data. Self-training uses pseudo-labels, as the programs in pBest are only approximations of the true ground truth programs for X star. Latent execution self-training, or LEST, is a related PLAD method. Similar to self-training, LEST first constructs Z as the current best program set, pBest. Then, differing from self-training, LEST constructs X as the executed version of each program in Z. By construction, the labels in Z will now be correct for the paired shapes in X. The downside is that X only approximates the distribution of shapes in X star. The final PLAD method we consider is wake-sleep. Wake-sleep first trains a generative model, PZ, over the distribution of programs in pBest. Then it can create paired XZ data by sampling new programs from PZ and recording their executions. Like LEST, the Z program labels are by construction exact matches for their paired shapes, but X is once again only an approximate distribution. PLAD methods can be combined while fine-tuning a single recognition network. We first construct distinct XZ distributions for each PLAD method. Then, during training, each batch is randomly sampled from one of the paired distributions. We run experiments across three shape program domains: 2D and 3D constructive solid geometry, and shape assembly, a domain-specific language for 3D shape structures. PLAD fine-tunes a pre-trained recognition model towards a distribution of interest, leading to inferred programs that better match target shapes. We compare test set reconstructions from the combined PLAD method against other fine-tuning approaches, such as policy gradient RL and individual PLAD approaches. In all domains, the recognition model fine-tuned with the combined PLAD method achieves the best reconstruction metric improvement over the pre-trained model. On experiments for 2D CSG, we find that PLAD methods converge much faster than policy gradient RL. RL takes over 36 hours to converge, while PLAD matches its performance in less than an hour. We also observe that PLAD performs well even when training data is limited. PLAD, with 10% of training shapes, achieves better reconstruction error than RL trained on the full training set. Please find our full paper, code, and data at our project page. Thank you for listening.